In today's information age, we face the increasingly difficult challenge of harnessing a vast universe of electronic information. Query, search, and data retrieval technologies have not kept up with the enormous progress of data generation and storage technologies. In short, as our collections of data continue to grow, it is imperative that retrieval technologies keep pace. Otherwise, the result will be information overload. Today, we face two primary difficulties with data retrieval techniques. One is quantity. A search will often yield either no matches at all or far too many. The second problem is quality. This problem is illustrated when we need to sort results. Traditional tools give us many sorting choices, but applied naively, none of these sorting mechanisms will necessarily lead us to the results we care most about. While it's easy to sort based on a single criteria, like price or distance, there are generally many aspects that we care about when making a selection. The current paradigm for data retrieval is parametric search, also known as constraint-based search. The idea is that the system receives a set of boundaries on a particular criteria as input, and will return all data which falls between such boundaries. Conceptually, parametric search can be understood as drawing a box in n-dimensional space. The edges of the box represent the constraints, and the search will return all data which falls inside the box. Now we need to talk about optimization theory. Optimization theory teaches us that optimal solutions lie near the Pareto optimal frontier. This frontier represents the intersection of various graphs and planes and will coincide with a particular corner of a parametric search box. Thus, there is generally a corner of our box which represents an ideal solution. Returning to our n-dimensional box, we can see that once we identify our ideal corner, parametric search may struggle to find relevant results and find the right number of results. The search will find all data within the constraints, but it's quite possible that the optimal data lie just outside the constraints. Despite being very close to ideal, this data will not be found. To use a real example, suppose you're searching for a new car, a car which is perfect in every respect, but lies $1 above your specified price maximum will not be found. This is a fundamental problem with parametric search. By using hard constraints, it often fails to accurately model the way humans actually make decisions.
Our human-like intelligence technology is changing the face of data retrieval. This next-generation technology breaks free of the limitations of the parametric search box. The notion of the ideal or optimal solution remains behind, but the box disappears. This means our technology search can score records directly, based on distance from the ideal. By eliminating the box metaphor, a grid delivers more relevant results and can effectively control the number of returned results as well.
Our solution models the way humans actually make decisions, so it's readily adaptable to the complexity of real-world scenarios. In particular, our solution implements trade-offs.
When we search, select, or make a decision, we evaluate alternatives with respect to one or more criteria. For example, if I'm buying a laptop, I may care about CPU speed, weight, screen size, price, and hard drive capacity. The reality, however, is that many of these criteria are conflicting. If I want a large screen size, it'll probably make the laptop heavier. If I want a fast laptop with a big hard drive, I might have to pay more. In situations where we can't have everything, there's a need to trade off between various criteria. That is, define which criteria are relatively more important than others.
Our model is unique in its ability to handle these trade-offs intelligently. When we identify a criteria as more important, the axis representing that criteria will be stretched, thus making distance scores with regard to that particular criteria more significant. The ability to stretch and compress various axes gives our technology fluid control over the trade-offs, which are critical to any decision-making or search process. Our model goes above and beyond simply multiplying a weight by a score. It also incorporates a fully extensible set of functions to describe various criteria behavior. These can be thought of as utility functions, and they enable our model to fully depict the needs of a particular scenario. The extensibility of these functions ensures that our model has the widest possible range of applicability. We give users the flexibility to specify the nuances of a particular scenario. The interface is fully customizable, but let's walk through the components of a typical application using our model.
On the left, we see the criteria influencing this particular decision or search process. Next to each criteria is a weight defining its importance, and the criteria is scored with respect to customizable criteria behavior functions. On the right, we see the results for this particular decision or search. and these results are sorted according to their proximity to an ideal. This proximity can also be translated into a percentage score.
One last feature of our human-like intelligence technology worth mentioning is inference. Not only can our engine provide results given a set of trade-offs and priorities, it can also do the opposite. If we impose a result ordering on the engine, for example, by specifying a laptop we happen to like, the engine can adapt and learn from this ordering. Furthermore, it can tell us what particular combination of weights will give us the result set. Inference opens the door to an immense range of applicability for our engine. In breaking away from the traditional parametric search model, we are changing the face of search, data retrieval, selection, and decision process.